Now we are going to see in the following video the magnetic field produced by a current carrying loop. Okay, so first watch the video and then we will discuss about it. Okay.
So here's our 25 turn coil with the piece of plastic down the center. Now I'm going to sprinkle on some iron filings. I have sprinkled on some iron filings, and they're going to be randomly oriented. So now I'm going to apply a current to the coil, which will generate a magnetic field. And what will happen is that the iron filings will become magnetized and rotate along the magnetic field lines, so we'll be able to visualize the generated magnetic field lines. So now I'm going to turn on the current, and I might have to tap it a little bit to get the iron filings to rotate. Inside the coil, you can clearly see how the iron filings have rotated along the magnetic field lines. As you move away from the coil, you can see how those field lines start to spread out. Now, if you look at the left edge here, you can see how those magnetic field lines form closed paths around the coil. In fact, any of these magnetic field lines will form closed paths, but you can't see that for some of these because as you get farther away from the coil, the magnetic field was not strong enough to rotate the iron filings.
We saw in the video that due to current carrying circular loop as shown in the diagram, the magnetic field lines are circular near the wires. Okay, as you can see in the diagram, the magnetic field lines are circular near the wires. Okay, and as we move toward the center of the loop, the magnetic field lines are straight or equidistant. Okay, and this type of magnetic field is known as uniform magnetic field. So we get nearly uniform magnetic field at the center of the loop, current carrying loop. Okay, there are certain points associated with the magnetic field produced by a current carrying circular loop. Okay, the first point is near the center of the current loop, the magnetic field lines are parallel and equidistant, known as uniform magnetic field. Okay, so at the center of this conducting loop, the magnetic field is uniform. Okay, it means the magnetic field lines are parallel and equidistant. Okay, and this is the uniform magnetic field. Okay, because the magnetic field lines are parallel and equidistant. Okay, the separations are equal, okay, between the magnetic field lines. So this is the uniform magnetic field, and this type of magnetic field is produced by the current loop at the center. Okay, the second point is at the center of the loop, the magnetic field strength B is directly proportional to the current I. Okay, mathematically we can write B is directly proportional to I. It means when we increase the magnitude of current, in the loop. Okay, then the magnetic field strength at the center increases. Okay, and when we decrease the current, the magnetic field strength decreases. And we can also write, higher the current, stronger the magnetic field at the center of the loop. Okay, note it down. Now the third point is, at the center of the loop, the magnetic field strength is inversely proportional to the radius of the loop, that is r. Okay, it means if r is the radius of the loop, okay, then mathematically we can write the magnetic field strength B at the center. Okay, so this is the magnetic field strength at the center of the loop is inversely proportional to the radius of the loop. Okay, it means smaller the loop or smaller the radius, stronger the magnetic field at the center. Okay, write down, smaller the radius, stronger the magnetic field at the center of the loop. Okay, note it down. The fourth point is, the magnetic field strength at the center of the loop is directly proportional to the number of turns in the loop. Okay, here in the diagram we have only single turn. Okay, when we increase the number of turns, then the magnetic field strength at the center increases. Okay, in direct proportion. Okay, so the magnetic field strength at the center of the loop is directly proportional to the number of turns in the loop. Okay, now come to the direction of magnetic field lines produced by a current carrying circular loop. So here the direction of magnetic field is given by the same rule, that is right hand thumb rule. At this point here, the current in the loop is flowing in upward direction. Okay, and according to the right hand thumb rule, imaginarily hold the wire in your right hand such a way that the thumb is pointing the direction of current. At this point, the thumb must be in the direction of current, then the direction of curling of your remaining fingers give you the direction of magnetic field here. So the direction of magnetic field is anti-clockwise. Okay, at this point. So I am I have put it the arrow in anti-clockwise direction. Okay, now come to this point. At this point, the current is in downward direction. So you have to keep your finger, so you have to keep your thumb in downward direction. Okay, then the fingers are curling in clockwise direction. So the magnetic field lines are in clockwise direction at this point. Okay, so you see that at this point the magnetic field lines are anti-clockwise, and here the magnetic field lines are clockwise. Okay, so in between the loop or in the loop, okay, in the loop the magnetic field lines are in the same direction. Okay, you can see that the magnetic field lines are supporting each other in the loop. Okay, and both are directed in the same direction. Okay, so this is about the magnetic field lines produced by a current carrying loop. Okay.